Right. Welcome everybody to this next session. It's very strange to do that when you don't see any faces, but I'll do my best. So this is the spotlight session. We have 12 papers to present. We have received 53 papers that are presented as posters, which have been published in highly ranked journals and conferences. I think it's a very good outcome for research coming from Catalonia. These are filtered, if you want, from all the research we have done over the last year. So if you have not seen the posters yet, the links to the material that the authors have provided is available on the web, and you should also have received the link to the Discord rooms where you can have a chat with the authors. As for the spotlights, which is this session, more than selecting the best of the best, which would be very difficult anyway, we have tried to select a good cross-cut of papers that represent works from different institutions, presented at a variety of forums, and also demonstrating the diversity we have in Catalonia in terms of people from different nationalities, gender, and everything. So I hope you'll enjoy this small sample of research originating in Catalonia. We have to kick into the session very fast because this session is very compacted. We only have 45 minutes and we're starting late. So we have asked the authors to do a 3-minute teaser presentation, and I will be very strict with that. If you can do 2 minutes, even better. As for the audience, if you have any questions, there are 2 ways to ask for them. If you have pressing questions, please keep them for the end of the session when we should have 5 to 10 minutes for Q&A. And you can either raise your hand or type in the chat indicating which paper the question is for. And we'll take as many as we can, depending on the time. And then if you want to discuss with the authors, the Discord rooms are probably the best option for that, through which you can have an asynchronous chat with the authors. So without any further ado, let's follow the order of the papers in the teaser session. The first one is going to be presented by Vacit, Oguz, Yacizi. And the title is Orderless Recurrent Models for Multilabel Classification. Yeah, so
hi.
You have Oguz?
I will share my screen now. Can you see it? Okay, so hi everyone. I'm Oguz, and our paper is called Orderless Recurrent Models for Multilabel Classification. So as you know, for multilabel classification, binary cross-entropy based approaches work quite well. But in recent years, people also start using RNNs to model label relations in a more explicit way. But the problem is that RNNs require sequential input. So therefore, you have to input your labels in a sequential manner. And since multilabel classification is an orderless task, you can pick any order that you want for the labels. So this leads to a problem, which is if the order of the predictions is not aligned with the order of the labels that you have, although your predictions are correct, there will be loss, as you see in this image, for example. So therefore, in the initial works, authors propose to impose fixed orders. So like they always, the order is always same, it never changes, and the model learns to output in the same order. So what they do basically, for example, they sort the labels according to frequency. For example, for frequent first approach, they first put the most frequent class, and afterwards less frequent classes follow. And for the rare first approach, it's the other way around. But also we think that this is a little bit problematic because, for example, in this image that you see here, the labels are frisbee and dog, but the visual evidence of the dog is much bigger compared to the frisbee's visual evidence. So it's highly probable that the model will try to output dog in the first time step instead of frisbee. But the gradients will try to push this dog prediction to frisbee. So because of the label order, imposed label order. So because of that, we call these misguided gradients. These gradients will cause, will hinder the convergence and also will make training more difficult. So because of that, we propose to choose the ordering that minimizes loss. We don't impose any fixed order, so we dynamically order the labels to get the minimum loss. So we do it in 2 ways, which are called predicted label alignment and minimal loss alignment. So our approaches yield lower losses than the fixed order approaches, and also it converges in fewer iterations. So at the end, also they surpass the other CNR and fixed order methods. And when we compare our results with the state-of-the-art results, we highly surpass the other results in 3 data sets, and we get competitive results on the 4th data set. So if you have more questions, please let me know, and thank you for your attention.
Perfect, thank you very much. If you have any questions, please keep them for the end. Let's go on then with the second paper that will be presented by Ciprian and Adrian Corneanu. The title is Computing the Testing Error Without the Testing Set. Ciprian? Perfect, we can see your screen, we cannot listen to you. You're muted.
All right, do you hear me now?
Yep, that's fine, thank you.
All right, so computer vision is concerned with tasks like object recognition, automatic interpretation of facial expressions, and image segmentation, among many others. And to determine which computer vision algorithms are better at each of these tasks, we typically rely on large manually annotated datasets. However, performing well on any given dataset is not the same as solving any specific vision problem. So we are all familiar with the concept of overfitting to the training data. Overfitting to the testing data is less known but equally common. Consider, for example, the topmost plot in this slide. Given a finite set of training samples, shown here as red dots, there is an infinite number of functions that map the input variable to the output variable. Depending on the algorithms we use, we will end up with one solution or another. But which of these results will best generalize to unseen testing samples? The answer is, it depends. This is shown on the bottom three plots, where the function that yields better generalizations are given. Note that the function that generalizes best actually changes as the testing data varies. So change the testing data or evaluation criterion, and the generalization gap between training and testing changes too. So is there a better way? We show that it is indeed possible to estimate the performance of modern computer vision algorithms even without the need of a testing set. Deep nets that generalize have specific functional connectivity patterns which differ from those observed when the network memorizes training samples. As shown on the left image, memorization is indicated by local activations of a small number of nodes in each layer. Think about this as the network using a tiny number of local parameters to memorize a sample while using other local parameters to memorize another. In contrast, when a network generalizes, its functional pattern, activation pattern, involves a large number of parameters distributed across the whole network. That is, every sample activates a similar large number of nodes distributed across the network as shown on the right. We note that when a network memorizes samples, the topology of its activation binary graph yields a simplicial complex with few or no holes, whereas when the network generalizes, the topology of its functional graph has many holes. So we use the creation and destruction of these functional holes to determine whether a network has learned to generalize to unseen samples. We measure generalization using the average life and midlife of these functional holes. And for a network to generalize, we wish life to be as large as possible and midlife as small as possible. This is shown in these results. On the first row, we plot the average life of functional holes against the generalization gap. On the second row, we plot inverse of midlife of functional holes against the generalization gap. Note that as the generalization gap increases, life and inverse midlife of the network decrease. And this is independent of network or vision problem we have tested. So our proposal is that in order to evaluate their algorithms, researchers and practitioners use the approach summarized on the screen. First, you train your deep net with your training set. Then you can compute the topology of the functional graph and estimate the generalization gap using the algorithm we provide. If the estimated generalization gap is large, you need to change the network's topology, loss function, or use a larger training set. Make the appropriate modifications and repeat the process until the generalization gap estimated by our algorithm decreases sufficiently. Then you can use a sequestered testing dataset to verify that indeed the generalization gap is as good as expected. If confirmed, you're done. You now have a network that has learned to generalize to unseen samples. Thank you.
Thank you, Ciprian. The next paper in the list is going to be presented by Yaxing Wang, and it's called MineGAN, Effective Knowledge Transfer from GAN to Target Domains with Few Images. Okay, we can see your screen, we cannot listen to you. No, we cannot listen to you, Yaxing.
Oh.
Okay, now it's better.
Hello?
Yes, okay.
Okay. Our paper is about how to effectively use the transfer knowledge from the pre-trained GAN. So to find pre-trained model.
It seems like the audio is coming in with cuts. I don't know if you're moving your microphone or it's a network problem.
Some problem?
Try again.
Now it's
No, you're being cut.
mode now open.
Okay.
Can
No, I'm afraid we listen half of the words that you say. Shall we go on to the next presentation and try to figure it out and maybe resume at the end? Are you okay with that? You're saying?
okay, maybe go to the next one.
Okay, let's give it some time then. Let's continue with the fourth paper and then we'll go back to Yaxing at the end. So if Noah is in the audience, Noah Garcia, she will be presenting a paper called Knowledge-Based Video Question Answering with Unsupervised Scene Descriptions.
I think she's not inside the room anymore.
Okay, go on with the fifth paper. Kang?
Yes, Lei.
If Kang is in the audience, he's ready, we can go
Yes,
on
he
with
is.
the paper. Perfect. So Lei will present a paper called
Hi.
GANwriting, Content Condition Generation of Styled Handwritten Word Images.
You can see my screen, right?
Yeah, and we can listen to you. That's good.
Okay, so our work is GANwriting, content condition generation of styled handwritten word images. And actually we're doing, try to do the handwriting text generation based on the calligraphic style information and both textual content information. And here's our architecture. So we have two inputs here, and the first input is images, which try to provide handwriting style information. So for the images here, we don't care about the content, the text. And the second input is text strings, and we take it from external just a text string, a text corpus. It can be out of vocabulary words from the data sets used here. So here we have a style encoder, and to get some style information here. And here we have a content encoder, try to get content. And then we have two pipelines. So one is go through here and try to concatenate both style and content information, try to initialize the generating process. And another one is we try to make the content information just into reshape into a long single vector and try to make use of them to do the make use of the adaptive instance normalization. Try to inject the content information into the generator. And X bar is a final output, which is guided by 3 losses. The first one, discriminator loss, is try to make the generated images to be realistic in general. And the second one, reticle classifier, is try to make the generated images to look specifically to a specific writing style. Because here we have like more or less 600 letters, and just to try to align it with a specific one. And the last one is a word recognizer, sorry. And it just focused on the content itself and try to make the content readable and aligned with the text strings as the input. And yeah, here is a more detailed recognizer. So in our experiments, we have tried the interpolations in the styles. So given style A and style B, and we are trying to traverse from A to B, something like this. And also we try to traverse in the content level, but it's as the text strings are discrete, so we try to change 1 character at each time step. So we can change from 3 to 7. Okay, and finally we have a human evaluation study, and the most interesting part is here, like we have a false positive rate of 55% something. So it's like over 50% the generated images were judged as the real ones. So that's, I think is fun. So finally, yeah, just something like this. And if you have any questions, just ask. Thank you.
Thank you very much, Lei. I don't think Noah has appeared yet, so let's continue with the 6th paper. It's going to be presented by Paul Rodriguez, who's connecting from Canada. Thanks for joining us. And the paper is going to be Embedding Propagation, Smoother Manifold for Fuse Shot Classification. Is Pau available? Okay, Nuria, can we make Pau a presenter, please?
Yes, one moment. I can't do it. I don't know why.
All right, technical problems.
Yes.
So let's continue. Okay, we'll come back to Pau later.
Okay.
Let's continue with the 7th paper. Raquel Gil. Let's try to make Raquel a presenter then. And Raquel will be presenting, if everything works, her paper on color matching images with unknown nonlinear encodings. Okay.
Hey there, can you hear me?
Hi, Raquel. Yeah, we can see you. If you can share your screen, you can start whenever you're ready.
Is it good?
Perfect.
Okay, right. Yeah, I will present our work, and this was done during my PhD in UPF. First, let me introduce the digital camera color pipeline. So the light goes through the sensor, and then the inside the camera goes through several processes till we get our nonlinear image. We can describe this pipeline as follows: a linear transformation that carries the color information and a nonlinearity. This nonlinearity usually is a gamma correction, but current professional cameras might use logarithmic curves or a combination of both. So while shooting a film, several images are taken from the same scene from different perspectives. But even when we use the same camera, we might have images that differ in terms of color, and it is necessary to match them. And this is exactly color stabilization definition. We have a reference and a source, and we want to match the colors of the source into the reference to get the color stabilized image. As I said before, we have like amateur and professional cameras that use gamma corrected curves, gamma curves and logarithmic curves. And our goal is to be able to match the colors from different non-linear encodings. And we are going to do that with a 3-step method. First, we will apply a power 10 if the images are log encoded to make them gamma corrected. Then we will apply a modified version of a TIP of 2014, which estimates a matrix and 2 gamma values. And then after, we will undo the first step, if necessary, with a log 10. We evaluated our method considering all the possibilities with gamma and log encoding for reference and source. And we compare it against several metrics and methods. Here are some results for gamma corrected. We can see here that, for example, in Gil et al. Method, the grass is still much brighter than in the reference. And it was also interesting to show what happens if, for some methods, we apply also the first step of our algorithm in log encoded images. Then we can see the improvement of the original method of Park et al. When applying the power 10 function. And finally, I would like to show that this method works in real scenarios. This is ARRI footage. Those are HDR encoded images with different non-linearities. And the idea of using color stabilization can be applied to create also high dynamic range images from non-linear outputs, as well as using it for multi-camera lighting imaging, where several images are taken from the same scene. And thank you so much for your attention.
Thank you very much, Raquel. I think Pau is ready to present, so maybe we can go back to paper number 6. Is that right? Hi, Pau. So
Right.
Pau Rodriguez will be presenting his paper on embedding propagation, smoother manifold for few-shot classification.
Can you see my screen?
Yep, perfect.
Okay. Perfect. So thanks for inviting me. I'm Pau Rodriguez, and I'm going to present our latest work on few-shot learning. This is joint work with my colleagues at ElementAI. As you know, few-shot methods learn an adaptive algorithm like matching images instead of memorizing class information. And as a result, we only need 1 image per class instead of thousands of them. However, the main challenge of few-shot classification is that the train validation and test set are disjoint and there is a big generalization gap. So the key insight in our paper is that we use this idea that smooth class representations improve generalization, and also they are better for semi-supervised and transactive learning. For instance, manifold mix-up, which is another technique, improves generalization by leveraging interpolations between samples in the input and output space. However, manifold mix-up is fully supervised and it's applied to all the layers in the network. In our work, we propose embedding propagation, which is a technique to smooth the class representation manifold in order to improve generalization. Embedding propagation is unsupervised and non-parametric, and you can place it at the top of your feature extractor. It works best combined with transductive learning algorithms like label propagation. In fact, embedding propagation is based on label propagation, and the label propagation is an iterative algorithm that propagates label information through a graph of labeled and unlabeled samples. In experiments, we show that just by placing embedding propagation on top of the feature extractor, it greatly improves the generalization of our models, getting state-of-the-art performance. We have consistent results in 3 different architectures and across like 4 different datasets. And in semi-supervised learning, we get consistent results. And this is consistent with the fact that manifold smoothing helps generalization on semi-supervised learning. And finally, to show that really our method is doing smoothing. We interpolate pairs of embeddings of two images belonging to two different classes, and we see how the class boundary changes, the class probability of each of the classifier. And at the left, you see without embedding propagation. At the right, you see with embedding propagation. And you can see that embedding propagation achieves smooth transitions between the two classes of embeddings we interpolate. So to conclude, we have presented an unsupervised non-parametric algorithm for smoothing the class representation manifold, which improves transductive and semi-supervised visual learning and achieves state-of-the-art results. And finally, just say that you can add it with 3 lines of code to your model if you want to try it. And if you want to know more, you can read our paper, or I welcome you to also access to our GitHub. Thank you.
Perfect. Thank you very much, Paul.
You're welcome.
So let's continue with paper number 8. Yi Xiao will be presenting a paper on multimodal end-to-end autonomous driving.
Yes. Let me share my screen.
Good.
Can you see my screen?
Not yet. Yes, we can.
Okay, nice. Let me just. Okay, hello everyone. My name is Yi Xiao. I'm currently a PhD student at Computer Vision Center. My supervisor is Antonio M. Lopez. Today I'm going to present one of our work, multimodal end-to-end autonomous driving. Nowadays, there are different paradigms addressing the development of artificial intelligence models in autonomous driving. On the one hand, we find modular pipelines which divide the driving into some subtasks such as perception, manual planning, and controller. On the other hand, we also find end-to-end driving approach that try to learn directly mapping from the input road sensor data to the control signals. In this paper, we focus on the later one, end-to-end autonomous driving. And most proposed method use RGB image as the input sensor data. But we think that an autonomous vehicle is usually set not only with the cameras, but also some active sensors such as LiDAR that could provide the depth information. So in this paper, we analyze whether combining the RGB and the depth image, which means using RGB-D data, could produce better end-to-end driving models than relying on a single model. We took the conditional imitation learning model as our baseline model. This model takes the image and the speed as the input and use the high-level comments as a branch selector to directly output the vehicle control signals such as steering angle, gas, and the brake. For the two single modal models, but besides training models with RGB image, we also try to train models using depth image as the input. Note that here the depth image could come from an active sensor such as LiDAR or a monocular depth estimation model. We include both cases of experiments in our paper. As for the multimodality, we firstly input the RGB-D image from the perspective of early fusion, like this model. And then we also explore the mid and the late fusion schemes. Since the time is limited, I will not show too many details in the presentation. Overall, our experiments clearly allowed us to conclude that multimodality is indeed a beneficial approach for end-to-end driving. Here I will show you a small demo for showing the driving results in color simulator. We will show 2 turns results, turn 1 and turn 2. The left turn 1 was used for collecting the training data set, and the turn 2 is unseen for the model. We show the comparison of two single, We show the comparison of two single modality trained with RGB or active depth image with multimodal models trained with RGBD image in the early fusion scheme. We could see that with only RGB image, the model is more difficult to detect preceding vehicles, so it collided to the preceding car. However, by adding the depth information, the model performed much better. This advantage of RGBD model is more experienced in the new environment. We could see in the new environments, no matter in making turn at intersection or detecting the preceding vehicle or detecting the pedestrian or avoiding the effect of strong sunlight, the RGBD models perform much better than the single modal models. Like here, detecting the preceding car, detecting the pedestrians, and also the effect of the sunlight, strong sunlight. Yeah, this is my presentation. Thanks for your attention.
Thank you very much, Ian. We'll go on with the next paper. It will be presented by Adriana Fernandez. The title is GANs for Unsupervised Visual Speech Adaptation to New Speakers. Hi, Adriana. We cannot hear you. You're on mute. Okay, that's better. Yep.
Okay. Can you see my screen?
Not yet.
Okay.
Okay, that's fine now.
Now?
Yep, thank you very much.
Okay, I'm Adriana and I'm presenting GANs for unsupervised visual speech adaptation to new speakers. So the goal of this work is to target natural speech of any speaker. However, speaker-independent systems are still dominated by the audio modality. And also it has been shown that visual speech recognition is more consistent in speaker-dependent scenarios. So what we propose is to investigate the visual adaptation of a speaker-independent system to a new speaker. In particular, what we propose is to jointly solve both tasks, the speech recognition problem by constructing a robust audiovisual speech recognition system using data from audio, video, and annotations of multiple speakers, and also the speaker adaptation problem by explicitly adapting this speaker-independent system to an unseen speaker, but using only data from video samples of both domains, the multi-speaker domain and also the unseen speaker. So which is our assumption? Our assumption is that in an ideal speaker-independent system, the same speech events should be represented in a similar way. So as you can see here, this is independently of the speaker. So as you can see here, there are two different lip positions. And what we expect is that the first lip position is represented, for example, as feature 1, and the second lip position as feature 2. However, the problem is that video frames from both domains correspond to two different marginal distributions, where no correspondence between samples is available. This means that we don't know when the same speech events are being said. So we don't know when the same lip positions are being said. So what we propose is to use coupled generative adversarial networks, or GANs, to learn this joint distribution. This joint distribution will be useful to minimize the distance between the features of corresponding lip images. I'm showing here the whole system. Just to sum up, the speaker-independent system is a sequence-to-sequence model with two encoders, one audio encoder and one video encoder, one decoder, and two attention mechanisms. Here in this side, I'm showing the GANs, where the two networks are connected by sharing the same parameters between the discriminator of the multi-speaker case and also the visual front end of the video encoder. So how do we adapt the system to the unseen speaker? by iterably minimizing these two losses. So finally, I wanted to show some results. So here we compare 3 systems, an audio-only system, an audiovisual system, and our adapted audiovisual system. These systems are exposed to different signal-to-noise ratios. And as you can see here, we obtain an 15 overall character rate improvement with respect to the audio-only and a 10% improvement with respect to the audiovisual. So just to mention that to the best of our knowledge, we are the first to propose the adaptation of the visual front end of a speaker-independent system to an unseen speaker. So if you want to know about more details about this work, please read the paper or send me an email. And thank you for your attention.
Thank you very much, Adriana. Let's go on to the 10th paper of the session by Miriam Belver, called A Mask-Guided Sample Selection for Semi-Supervised Instance Segmentation.
Hi. Okay, can you see my screen?
Perfect, yes.
Okay, so hi, my name is Miriam and I'm going to present this work about mask-guided sample selection for instance segmentation. So our motivation is that fully supervised models for instance segmentation typically require pixel level annotations, which are very expensive to obtain. So some alternatives are weaker forms of supervision, such as weakly and semi-supervised methods. And in our case, we are going to focus on semi-supervised ones, which leverage a large amount of unlabeled or weakly labeled data, together with a limited amount of strong labeled samples. So this work that we are presenting is an extension of a previous work of ours, where we presented a pipeline for semi-supervised segmentation. So this slide shows our setup, which consists of having 2 different networks. The first network, that we call annotation network, is trained in a fully supervised way with a limited amount of strong labeled samples, which are very expensive to obtain. So following, this network is used to pseudo-annotate samples that are unlabeled or weakly labeled, so we can obtain pseudo-labels for free. Finally, we have a second network that we call segmentation network that we train with both these strong labels, which are expensive, and also these pseudo annotations that we obtained for free in the previous step. And this segmentation network is the one that we use for getting our final performance. So in this semi-supervised pipeline that we just presented, we chose which samples to strongly annotate in a completely random way. So in this work, we wanted to improve this strategy, and we proposed a novel active learning mechanism to choose which samples to manually annotate in order to lead to a better performance. So our setup consists in having very few strongly labeled samples and a larger amount of weakly labeled ones that have image level tags as the one you can see in this slide. So we first train the annotation network with these very few strong label samples that it's in the order of only 100 images. And with this model, we predict for each weak label samples an estimation of how good the current model is for that image. So later we choose which samples to strongly annotate based on this confidence score. So our way to estimate the performance of the current model for a given sample is estimating the intersection over union between the predicted and an hypothetical ground truth mask for each object in the image, as you can see in this slide. So we analyzed which IOU scores led to higher performance, and we saw that these were the scores around 0.5 of intersection over union. And then we visualized which images are related to each score. And we saw how lower scores are assigned to complex images, which could be considered outliers for this dataset, that is the Pascal box. And on the other hand, higher scores are assigned to easy images that probably the model wouldn't learn anything new from them, because the model is already good at segmenting these kind of images. So finally, in this plot, we show the segmentation quality achieved at different annotation cost for our mask-guided strategy compared to random selection for the annotation network for different budgets. And we see that our proposed scheme improves performance. So that's all. Thanks for your attention.
Thank you very much, Miriam. Let's go on with the next presentation. That's going to be by Jordy Janemola, on fruit detection and 3D location using instant segmentation neural networks and structure from motion photogrammetry.
Hello, do you hear me?
Hi, Jordy. Yes, a bit low, but yes.
Okay, I'm going to try to share my screen as well.
And please speak closer to the microphone.
Yes, do you hear me well now?
Yep, okay.
Okay, perfect. So hello, I'm Jordy and I'm coming from the University of Lleida. And in this work, we combined instant segmentation neural networks and structure from motion in order to detect the fruits in images and then 3D locate them in the space. Sorry. No. Yes. First of all, we acquired the data in the field. We scanned a total of 11 trees, and we took different pictures in order to build the 3D point cloud using structure from motion. And after that, we annotate this point cloud by placing 3D bounding boxes around each apple. Here you have the methodology pipeline, which consisted in first applying instant segmentation in the images. And after that, we remove the pixels that belongs to the background because we are only interested in generating the 3D model of the apples, of the object of interest. After that, in order to count the number of apples in each tree, we project the detections from each image onto the 3D space by following the pinhole model. In this slide, you can see the results. Here there is the instant segmentation results in the images and also the instant segmentation results in the 3D point cloud. And as you can see, when applying the structure from motion, the results improved. And this happened because due to the multi-ball approach, which is based structure from motion, the number of fruit occlusions decreased because the fruits that were occluded from one image could be disoccluded from the other point of view. And also the number of false positive decreased when applying structure from motion because only the false positive that are appearing in more than one image are going to be modeled in the 3D space, and this is not likely to happen. Here you have some results in 8 trees. Here you have the sun and then the apples located. You have here a link where you can interact with this point cloud. And the main conclusions is that due to the multi-view approach on which is based structure from motion, the methodology presented a small number of fruit occlusions, also reduction of false positives. And the main disadvantage is that this methodology cannot be used in real time due to the computationally intensive operations of the structure from motion. That's all. Thank you for your attention. If you have any question, please contact me to this mail because now at 2 I have to leave in my class and I cannot wait until the end of this session. Thank you very much.
Perfect. Thank you, Jordy. Let's proceed with the next paper. That's going to be by Maria Gonzalez on curriculum learning for recurrent video object segmentation.
Yes. Hello.
Hi, Maria.
Perfect. Can you see the screen?
We can see the screen. We can listen to you.
Perfect. Hi, my name is Maria Gonzalez, and I'm going to talk about curriculum learning for recurrent video object segmentation. Our work focuses on the study of the impact of curriculum learning, which consists of starting training your model with simple concepts and increase the complexity through time. We have studied 2 strategies applied to the dataset for autonomous driving kitty mods and using the Arbos model, which provides a fast solution for this challenge. The addressed task is one-shot video object segmentation, where we have a video sequence separated in frames, and we want to track the objects of interest. So with one-shot, what we do is we provide to the model the mask of the first appearance of the object, and then with that information, the model has to estimate the segmentation on the remaining frames. We have tested these 2 strategies on 2 sets of experiments, the one with larger image resolution but less images per training batch, and the second one with more compressed images but with more images per training batch. And Our first strategy has been scale sampling. Scale sampling is a strategy that benefits from using the ground truth annotations as input on the following step, but at the same time it avoids the discrepancy that we could obtain between training and inference. To avoid this discrepancy, what it does is it starts training with the ground truth annotations, but then we change to use the model's outputs. We have studied two decays, the linear and the step, and for both of them, we have studied the straight definition of scale sampling, which is forward, and also the inverse strategy. And we have been using the forward step as the baseline model, as Arbos, the used model, was trained originally this way. Results show that the best performance is obtained when we use an inverse step with higher image resolutions. The second strategy is frame skipping, where we subsample a video sequence in order to expose the model to sequences with faster changes. We have proposed two curriculums in which we increase the number of skipped frames through time. And for each of them, we have two methodologies in which we apply frame skipping during all training time or only during the first half of training, because we were using the forward step scale sampling as baseline, so we had two differentiated phases of training. And our results show that the model benefits from using this strategy, but only when we apply frame skipping during the first half of training. Furthermore, the combination of the best implementations of frame skipping and scale sampling has resulted in a higher improvement of the model's performance. Thank you very much for your attention.
Thank you, Maria. Yaxing, do you want to try again? Maria, could we give Yaxing Wang a second chance if we can hear him?
Hello.
Hi.
Hi. Let me try again.
Okay.
Share.
Now it seems like we can hear you fine.
Yeah, change please in CVC.
Perfect. So Yaxing Wang will present his paper on MineGAN, effective knowledge transfer from GANs to target domains with few images.
Okay. Now it's okay? Everything is fine?
Yeah, now it's fine.
Okay. Basically, is it the paper we want to use the constraint model for image generation? So basically, current method transfer GAN is direct to fine tuning to the constraint model. So this method have the problem is it will suffer from overfitting. So in this paper, we try to reduce the overfitting. So to combat this challenge, we propose a new model with a new modality, which is the miner. So the function of the miner is to localize the latent space, which is close to the target domain. So in this case, we can reduce overfitting because we first localize the important latent space and then to fine tuning. And second motivation is like we explore how to use the multiple GANs. And then we also propose a selector which help us to localize which generator as the final output. So for the framework, we have two frameworks for single generator and multiple generators. Multiple generator means we have multiple models. Let's see the single generator. Basically, in our method, we have two stages. The first stage, we only train the miner and the discriminator, and we frozen the generator. So this aim to localize the latent space. And second stage is we also update the generator after the miner and the discriminator get convergence. So for the multiple models, we propose a new way how to train the miner and discriminator. So basically, the key idea is like here for when we do forward and back propagation. Every time we only update one miner. For example, here we have a manners, but when we do back propagation, we only update one manner. So how we select which manner we update? So basically, we use as the output of this commenter. Basically, we take the output manner and then set it into the generator. We get a figure image. So we check which figure image have the closed distribution with the real distribution, and then we only update the manner. For the disk commenter is the same. Because for this commenter, we need the real data and the figure data. So for the figure data, we use the same way to select which figure data to use to update the disk commenter. And in the test time, we use the selector to localize which generate the output as a final output. And here the selector is is statistics by the training time. So you first get the statistics and then use them in the test time. Here the first one is about a single model, and we train on the face data, and also from a mini to places. So basically, our method gets the best performance. And the last problem is for multiple models. At the left, we use the 2-point model, and the right experiment we use the 4-point models. So basically, the conclusion is similar. The introduced manner help the model get a better performance. Okay, that's all. So basically, in this paper, we introduced a new modality manner to localize the latency base, and also our method can be used multiple models and condition and unconditional GANs. Okay, thank you.
Thank you very much, Yaxing. There is a paper missing, which is the one by Noah Garcia. She was connecting from Osaka, and I don't see her in the audience. Just in case she's there. Are you here, Noah? I don't think so.
No, she's not.
Okay, so if not, is there any pressing question? We have gone already 20 minutes over time, so if there's any pressing question, please raise your hand. Raise your hand 1, raise your hand 2, raise your hand 3. Okay, so I think that you can direct your questions directly to the authors then, and let's close the session, thanking everybody who took on the effort to connect. I'll pass on to Maria for the closing and award session. Thank you very much. I don't know if Maria is in the room.
Okay, hi.
Hello.
Hello.
Over to you.
Okay, thank you. So we are arriving to the end of this long day, and we have been working backstage, trying to collect all the marks that we have been receiving from all the committees. That was pretty hard, and we could put everything together, and we ordered, and we make like a ranking of all the students. I have to say that has been an honor to see this spotlight session with so many young people with such amazing works, and it was nice also to see all the students of the master in the list. So no more words. People is tired, so let's go. Let's try to put on the table who is the people that got the best marks in these years. Some of them did the master in 2 years, some was full-time, part-time, etc. So I will start with us every year with the top 5 students. The first one is Mark Perez Quintana. I will ask him to switch on at least the face in order that at the end we have a nice picture of all the people. That would be nice for us. Okay. Nuria, can you help me with getting all the people in the
Yes, I'm doing it.
Okay, great.
Mark is inside.
Okay, Mark, thank you. If you can switch on your camera in order that at the end we have the picture of the 5 of you. Hi, Mark. Nice. The top 4 student is Maria Gil Aragonés. I think she's not there because she presented her master dissertation in July. So she has done an internship during the master in Sadako, and she did a nice project in July. So I saw that. I think she's not there today. So congratulations. We will send it to her. I
think she's in the audience.
Is in the audience, Maria?
Yes.
I checked it before and she wasn't there. So Maria, if you can switch on your camera, that would be great.
No, she's not.
Maria, there are several Marias.
Yes, she is. She just responded.
Yes, she is.
Okay, great. So switch on your camera. It's going to be great.
Okay.
So I move on while you, Nuria, are doing this, okay? So the top 3 student is again another Maria, is Maria Vila Abad. I saw her there. Great. It's amazing, huh? A lot of women in the top. That's really, really, very, very good. Hi, Maria Gil. Nice to see you again. So now Maria Vila is coming. Great. Okay, the top 2 student is again a woman, Sara Lumbreras. Sara, if you can switch on your camera, at least we will have this memory, no? We can take the full picture of you together. Hi, Sara. Very nice, congratulations. And the top 1 student that I was expecting this is Oscar Mañas. Oscar Mañas is in Montreal, actually. He's doing an internship at ElementAI with Pau Rodriguez that he presented. Hi, Oscar.
Hello.
Good. So please, if you want to switch off on your microphone and say something, that would be great. No words. I know this is difficult for you, but I have to say that it's a pleasure for us to be in this master with such good students. So there are already some companies today that are trying to contact some of the students. So we are happy and congratulations. Okay, hope to see you very soon, and I would like to keep you in touch in order you can explain us what are you doing in the near future. You and all the students, for sure. We are lucky having such good students. So don't move, because now we are going to move to the usual award that we give, that is the award to the best student, to the best master project. Okay, and this year, that is not very usual, we got a big 5 draw. Okay, so the best master dissertation was a big draw of 5 students. Some of them are already here. So congratulations to Laura Mora, Maria Vila again, Sara Lumbreras again, and Oscar Mañas again, and Joaquim Comas, that I don't see him, but probably is there. So Laura Mora, if you want to switch on your camera, you will have the memory of, Laura, good. So nice to see you all. Okay, so congratulations. We hope you have a lot of luck, you and all the students. It was not easy, it was a hard and long year, but I think we expect that from the coordination, we expect that you have learned a lot of things, and now you are happy to start again in a new project. Okay, so thanks a lot, everyone. For us, this event can be closed. So congratulations to these students and all the students in the master, and we hope to see you next year again in this event. Okay, thank you and bye, everyone. Bye.